Suppose a professor, he administers an 8-point quiz to a small class of 4 students. Let's say their name is A, B, C, D. And these are their scores. A scored 2, B scored 6, C scored 4, and D scored 8. Assuming that these 4 students, they are your entire population. That's it. There's nobody else in your population. These are the only 4 students. Now, here, the histogram graph of your population is uniform. You can take a look at this thing and you can draw that too, by the way. So, see, my 2, there is only one 2, right? So, this is you draw a line like this for 4, there is frequency is 1, for 6, frequency is 1, for 8, frequency is 1. So, it looks like this right here, which is exactly uniform distribution. Okay. All right. Suppose I take an ordered samples of size 2 with replacement from the above population and compute their mean. So I'm doing it right here. Okay, this is where this process is done. So I take a sample 2 comma 2, and the mean for 2 and 2 would be 2, right? The mean for, if I take another sample, let's say 2 comma 4, the mean would be 3. You can determine that 2 plus 4, right? Divide by 2, and the answer is 3. This is how you calculate your mean. Okay, same thing. Let's say I pick another sample 2 6, and the mean is 4. 2 8, and the mean is 5, and I can keep going like this. So these are my mean values. Okay, these are all my mean values, and this right here, these are my samples. Okay, these are samples I'm picking. So I'm going to be focusing on these ones right here. All right. By the way, on a side note, ordered sample means that the sample score for 2 4 and 4 2 are considered different. They are not one. So this 2 4 right here, okay, and this 4 2, they will be considered as two separate samples. Okay, the question is this: what is the shape of the sampling distribution of the above sample means? In other words, if you look at this number right here, these numbers, and look at these numbers right here, and if you write these numbers down, my question is, how do these how does the distribution of these numbers look like? Is it uniform? Is it going to be normal? Is it going to be right skewed or left skewed? This session is about answering these types of questions. This is central limit theorem. By the way, the answer for this is going to be normal distribution. So, central limit theorem, let's understand the theory first. So this is the official definition of your central limit theorem. Let x1, x2, x3, all the way up to xn be a sequence of independent and identically distributed random variables with a finite mean and a variance given by these expressions. Then, as your sample size increases, gets bigger and bigger, your sampling distribution of the standardized sample mean, which would be this right here, it will approach a standard normal distribution. And if you're feeling like this guy, it's okay. This session, I will help you understand what exactly it means. In simpler terms, it means this: that no matter what the shape of your original population distribution is, the distribution of the sample means will approximate a normal distribution as your sample gets larger and larger. So let's understand CLT through an example. Suppose you have a data from a population that has uniform distribution. This one right here. In other words, all the values between 0 and 1 are equally likely. And suppose I take a random sample of 4 points from this uniform distribution and I calculate its mean. So these are my 4 points: 1, 2, 3, 4. And I calculate the mean value of that. And I plot a histogram based on that mean value. And let's say this is my histogram. Well, I do it again. I take another sample of 4 points from the same uniform distribution, again calculate its mean, and then plot the histogram. So I do my 1, 2, 3, and 4 samples. Find its mean value, and I plot a histogram. This is my second one now. And I do it one more time now. I take another sample, 4 samples, 1, 2, 3, 4, calculate its mean value, and plot the histogram. Let's say it comes out to be this. And I keep doing like this for 1000 times. At the end, you are going to notice that your shape of your histogram will be almost like a normal distribution, something like that. This is the essential idea of your CLT. No matter the shape of your distribution, the distribution of your sample means would always come closer to the normal distribution as your sample size increases. So this right here, in this instance, I just picked up uniform distribution. It doesn't matter what distribution this is. This one is always going to end up as normal distribution. That's what it's saying. So this is the key idea of your CLT. The population can be anything. It can be your normal distribution, skewed, uniform, bimodal, or any weird shape, doesn't matter. If you randomly sample from it repeatedly and calculate the mean each time for those samples, then the distribution of those means will always tend towards your normal distribution. So let's say this is your population. It can be this distribution, your population can have this distribution, or this, or this, or this. Doesn't matter what the distribution is. So let's say you take 1000 sample. Okay, I'm just picking a number 1000. But if I keep repeatedly sampling 1000 samples and I take the mean of all those 1000 samples, so like I'm going to have 1000 mean. If I plot the distribution of those 1000 mean, it will always tend towards a normal distribution. It doesn't matter whether it's right skewed, or if it's left skewed, or if it's a uniform, or it's some weird shape. Doesn't matter that. It will always tend towards this shape right here, normal distribution. Now let's try to understand the effect of the sample size n on the distribution of sample means. So I start with the population that had a mean value of 2, and I picked up randomly picked up any distribution. In this case, I picked up this distribution. For this one, by the way, my standard deviation was 2, 2. So from this population, I randomly drew n equal to 2 data points. This was my sample size. Then I calculated the mean of these two values. Now I repeat this process 1000 times for each n equal to 2. Now this gave me 1000 sample means, and then I plotted the distribution of these 1000 sample means for my sample size n equal to 2, and this is the result I got right here. Then I repeat the same process for n equal to 5, 10, 30, and 50, and these are my corresponding results: n equal to 5, n equal to 10, 30, and 50. Okay, now I notice few things that as let's look at this n equal to 2 first. So here, look at my mean. My mean is 1.97, and this mean right here is 1.9, which is almost same as 2. My standard deviation in this case is almost 2. So this mean, if you look at this mean, this is almost same as your population mean. Well, what about your standard deviation? Well, your standard deviation is almost same as sigma divided by root n, which is sigma in this case is a population standard deviation. This is going to be 2 divided by root 2, right? Because this is your 2 right here. And the answer is 1.38. Well, let's look at this one right here. In this case, my n equal to 5. What is my mean? My mean is same as population mean. What about standard deviation? Standard deviation is population standard deviation divided by root n. This is going to be 2 because population standard deviation is 2 divided by root n is equal to 5. So root 5, and solving this expression, you'll come with this right here. And you can do the same thing with this and this. And let's look at this last one. In this case, my n equal to 50. My mean is 2.01, which is same as the population mean. What about standard deviation? This standard deviation is same as your population standard deviation divided by root n. Substitute your value of sigma, which in this case, population standard deviation is 2 divided by root 50 because my sample size is 50, and the answer would be 0.28. So the observation is this, that as my n becomes larger, when it becomes 50, the distribution of the sample means is normal. You can see that shape of the curve, it gets very close to the normal shape, right here. You see that? Look at this shape. When n was very small, it was not normal. When n start becoming bigger and bigger, it start taking a shape of a normal curve. You see that? Look at this shape. Okay, almost like a bell shaped, and this became more bell shaped than the rest of them. And the mean is 2. In other words, my mean, it has never changed. The mean of this and this and this and these are same as your population mean. And the standard deviation is sigma divided by root n. So your standard deviation is the population standard deviation divided by the root of the size of your sample. The standard deviation, it decreases with increasing n. Well, that makes sense because the standard deviation of these distribution of your distribution of your sample mean is sigma divided by root n. So as your n is increasing, this expression is going to decrease. Now let's understand the effect of the population distribution. So to understand this, I drew 1000 random samples from the exponential distribution. I start with exponential distribution first, and I calculate the mean for each one of these samples. And I plotted this distribution, which is right here. So this is my population, and this is the distribution of the sample means. And I noticed few interesting things. Number one, my mean actually, let's say in this case is mu for my population, and standard deviation for the population is sigma. They both are essentially 2, you can see that. And my mean again will came out to be mu. Okay, so the mean of my sample mean is same as your population mean, and the standard deviation of your sample mean was sigma divided by root n. And you can verify that actually this will be sigma in this case is 2, right? Your sigma is 2, so 2 divided by root n would be root 50, because my sample size is 50. I'm picked up 1000 samples, and each sample was a size 50. So 2 divided by root 50, and the answer is 0.276. Now look at the shape of my curve. It is almost normal distribution. And look at the shape of this curve. This is not normal, this is exponential. You see that? So, although this is exponential and you pick up 50 random points from here and you plotted the distribution of the sample means, it turns out to be normal distribution. All right, let's look at the another curve now. So in this case, I'm picking a normal distribution curve, and I drew basically I picked up 50 random points, okay, and I did this experiment 1000 times again, and look at my curve. It is still bell-shaped curve. In other words, it's still normal distribution. So this is normal distribution, my population is normal distribution, and my distribution of my sample mean is normal distribution. Now let's look at this one here. My population is almost look at this thing, it's a uniform distribution, right? Now look at this one right here. This is my distribution of my sample mean. It is almost normal distribution. All right. Now let's look at the next one. Here, my distribution is multi-model. You see that there are two models over here. It goes up and it goes up again, comes down. And my distribution of my sample mean, on the other hand, look at this. It is almost bell-shaped curve, right? Let's look at another one. In this case, look at this is a weird shape distribution. Okay, this distribution has some weird looking shape right here. All right. And when I drew 1000 samples, each of size 50, and I plotted the distribution of my sample means, and look at that. This still gave me normal distribution. Okay, let's pick up another one. Here, this is my Poisson distribution. Okay, now when I did the same thing, I drew 1000 samples from here, and I took size of my sample was 50, same 50, and I plotted the distribution of my sample mean, still came out to be bell-shaped curve or a normal distribution. Then I did the same thing with this one right here. I took a binomial distribution. Okay, this is my binomial distribution right here, and I plotted the distribution of my sample mean. Sample again was size was 50. I took 1000 samples, and you can see, look at the shape, still normal distribution. All right. So two important observation about the distribution of sample means. If your population mean is mu and population standard deviation is sigma, then as you take larger and larger samples of size n, as your n gets bigger and bigger, the distribution of your sample means it will be normal, and it is going to have following two characteristics. Number one, your mean of your sample means is going to be mu. We saw that. And your standard deviation of your sample mean is going to follow this right here, sigma divided by root n. Sigma is the population standard deviation. Okay, so the spread, which is this right here, shrinks as n grows. You can see that as n gets bigger, this thing is gets smaller. Okay, that's why the histogram they tend to get narrower and smoother. So let's take a look at this example right here. In this case, this is my original population right here, and I'm actually taking a sample size of 4. And this right here, this is my sample size of 4. All right. Oops, sorry, not this one. This one right here. This one. This one. This is my sample size 4. Okay. Then I took from the same distribution. Now I'm taking 1000 samples of size 15. So I'm went from 4 to 15. And you can see that my distribution curve, you see the spread just became smaller. All right, so this is my n equal to 4, and this where my n in this case refers to my sample size, is equal to 15. So when you go from 4 to 15, your spread in your distribution curve becomes less. In other words, it shrinks. Now back to our original problem. So a professor, he administered an 8-point quiz to a small class of 4 students. These are my students right here, and these are their corresponding score. Assume that these 4 students, they are your entire population. So if you draw the histogram, it will look like uniform. You can see that score 2, there is only one score 2, right? This one right here. How many score 4s are there? There's only one, which is right here. And same thing with 6 and 8. So the frequency of each one of these scores is 1. And you can see it's a uniform distribution. So the first question is this: how many ordered samples of size equal to 2 with replacement can you draw from this population? So in other words, how many 2, 4, and then 6, 2, like these types of numbers, how many can you draw from this population with replacement? By the way, it's an ordered sample. So ordered sample means that 2 comma 4 is will be different than 4 comma 2. So they would be considered as two different samples. Okay, and also verify the theoretical relationship between the population parameters and the sampling distribution parameters. We saw this relationship, so you have to verify this now. In this case, by mu x and sigma x, they are the mean and the standard deviation of the sampling distribution of your sample means, respectively. Your mu and sigma, they are the population mean and standard deviation, respectively. And your n equal to is the sample size. Also, examine the shape of the sampling distribution of the sample means and compare it to the shape of the population distribution. Now, the population here is 2648. These are the scores of all students. The mean of the population mu in this case is going to be you add all the scores and you divide by the 4 because that's your total number of that's the size of your population. Answer is 5. The standard deviation of the population is, I use the formula for standard deviation, and the answer comes out to be 2.236. Now, if I take all ordered sample of size 2 with replacement and I find the mean of each sample, then the distribution of the sample mean is shown right here. Okay, so this is, for example, take a look at the first one. This is 2 comma 2 because we are doing replacement, so you may come across with same sample twice. So 2 comma 2, and the mean is 2, right? 2 plus 2 divide by 2, and the answer is 2. All right, this is how you come with this 2 right here. Let's look at this one, 2 8. Okay, this one right here. So 2 comma 8, the average, the mean value is 2 plus 8, divide by 2, and the answer is 5. Okay, this is how you get this 5 right here. Okay, so these are by sample means right here. Okay, all these sample means. And these are my corresponding samples. And I'm going to get total of 16 samples. You can actually count 2, 2, 2, 4, 2, 6. These are my ordered samples. So the sample means, I just rewrote the sample means over here at the bottom. So this data right here is this one right here. Okay, then let's scroll down a little bit. Now let I create a table. This table actually is a frequency distribution of my sample means. So how many twos are there in my sample mean? There is a 2. How many twos are there? I write a frequency 1. You can actually go and check. Let me just remove everything. Well, in this case, there is only one 2. This one right here, right? There's only one 2. This 2. All right. So the frequency is 1. All right. What about 3? How many threes are there? Well, go back over there and count how many threes you got. 1 and 2. And that's it. Only two threes you got. This one and this one right here. So come back over here, and this is how you get 2. There are only two threes. Well, how many 5 you got over here? Well, it's saying 4. Let's go verify. Just come over here. You're going to see 4 5s. You're going to see 1, 2, 3, 4. 4 5s. Okay. And this is how this frequency table is created. Okay, from this, once I get the frequency table, from here I can draw the graph of my sample means. And in this case, you can see it is almost like a bell-shaped curve. Well, 2, right? How many twos I got? 1. So this is 1 right here. How many threes I got? This is my 3 right here. There are only two threes. And this is my 4. How many fours I got? 3 fours. How many 5 I got? 4 fives, from here. And then if you look at the shape, it's almost like a bell-shaped curve. Okay, now let's look at the mean of my sample means. My sample mean is this one right here. This is my sample mean. Okay, so let's look at the mean of my sample mean. You add all the numbers together, okay, divide by the 16 because that's the size of your sample means, and the answer comes out to be 5. This is exactly same as your population mean. The standard deviation of your sample means is going to be this right here. You can calculate the standard deviation and your answer will come out to be 1.581. So this is same as sigma divided by root, and sigma is your population standard deviation. Population standard deviation. And in this case, my n is 2. So population standard deviation is 2.236 divided by root 2, and the answer is 1.581, which is same as this. So the conclusion is this: the shape of the sampling distribution of the sample mean is a bell curve. Another word is a normal distribution. It's a normal curve. And the mean and the standard deviation of the sampling distribution of your sample means it satisfies this relationship. We just saw that it did satisfy that. Now let's take a look at an application of your central limit theorem. Imagine a factory that produces light bulb. These are your light bulbs. And we know that each light bulb, they have a lifetime, maybe in hours, and they want to determine the average lifetime of your bulb. We know that it's impossible to test every single bulb. That would destroy them all. So what the quality control team they do, they take samples. They take maybe 30 samples each day and they measure their lifetime for these 30 bulbs. So even though your population distribution of your lifetime might be skewed, okay, this is, let's say, your population distribution of your light bulbs. The central limit theorem, it says that if enough samples are taken, say maybe for 50 days, the distribution of your sample mean will be approximately normal. So if you take enough sample and you plot the distribution of those sample mean, it will look something like this, a bell-shaped curve. And from here, you can read the average value, mu. And you know the mu over here is same as the mu over here. So once you can determine mu from here easily, that would give you this mu. Because of the CLT with central limit theorem, the company can use your normal distribution to make predictions about its average lifetime. They can also calculate the confidence interval and perform hypothesis tests on the average bulb life. Without CLT, if you did not have CLT, you would need to know the true population distribution. For the most part, we really don't do that. We really don't know that. And this is why we use CLT.